Hey everyone, so in this video we want to talk about how to prepare geometry for Vellum simulations. So what we've looked at before is grids and grid-like geometries, which very often is what we have, but that comes with a couple of problems when we simulate that with Vellum. You can see it here in the shape, for example, and we talked about this before. We get this kind of stepping kind of deformation sometimes, which purely comes from the fact that this thing is built as a grid. And if I activate my light, because I have on my object level an environment light here activated, there it is. What you will also see later potentially in renders is some kind of faceting that comes from that. So maybe you can see that here if I move around, it can be subtle, but you can kind of see this kind of stripes on the surface. Up here you can see it as well. So if you just play around with a grid, you can find those kind of problems. And you will also be able to see it in the reflection. So maybe you can see that it kind of goes zigzag. And later on when you render this, this will be even more apparent. So here you can see it as well there. So all kinds of problems that can come from that, because in reality, cloth is actually not behaving in a grid-like structure, right? So what can we do about this? Actually, there is a node that is made by side effects particularly to make sure we have a better starting point, and that is called Planar patch. And what it does, and let's start it from scratch, just type in Planar patch, which is a bit of a weird name, but you will get used to it. And what this creates is something that is based on triangles and overall a lot more irregular. And this just is suited better for cloth simulations. So you can change where it is created just like a normal grid, and then you have the edge length here that defines how fine the whole thing should be. But again, even though it's built from triangles, they're also irregular in their nature. So overall you get a much more, call it chaotic topology. Now the difference in the look is not only do you get a little bit a different shape out of this, which is a bit more natural later on, because of course you will still see some kind of limitations of the geometry in form of wherever the bending happens, but it looks way more natural. And you can see here, this is now my planar patch based simulation. It's way more natural and it doesn't show itself as a CG object that much. And also you can see it a little bit in the reflections. Yes, you have irregularities, but they are more organic, let's call them, because they're not based on a grid. Especially when you have a light render, you can see a little bit better that the overall surface is not necessarily cleaner or anything, but because it's more irregular, it feels more natural. There is no, there are no lines, no clear visible grid, but more like a natural distortion on the surface. And this is why planar patch is better. Now, of course, you will not always work with a grid like this. You can actually change the shape to another form, like a trapezoid, for example, that then looks like this. If you change the numbers, and let's increase the edge length for now, so it's a bit faster. There you go. So you can change the shape. You can skew it. You can also taper it. So if you need a specific shape, you can totally do that with the built-in system in the planar patch. You can create a circle, of course, and you can also create a ring with all kinds of functions like the arc length and the size of the hole and all that. So there are a lot of different shapes actually built in. What we'll also see later on is you can create groups with a node that include all the points of the edges, which can be helpful later on so that you don't have to find them manually. And this is here under the seams, but we will look at this once we need it. Another kind of sister or brother node of the planar patch. So if you type in planar, you will find another one called planar patch from curves. And this is pretty cool because it takes curves as an input, and you can take any curve you want. For example, you could take that from some kind of blueprint or something, which can work very well if you have a very specific kind of cloth you want to simulate later. But you can also use just a draw curve. What I can do, of course, with a draw curve, and the only thing that is important here is that the curves that I draw should intersect. So I need something like this. And this is cool because I can now create a really complex shape relatively quickly that would be really hard to model. And if I feed this into the planar patch from curves, you can see I get an actual geometry out of this, a flat sheet of cloth based on the curves I gave it. Of course, this is a really crappy example, but I just wanted to show you how it works. And it's pretty cool that you can do that. And again, you can also feed that with curves from outside. Let's, for example, simulate that with a very simple example, just a circle that we turn into a curve that is open. And if we feed this in, of course, we get just a circle, which is not super helpful here, but you can see you can feed any kind of closed curve into the planar patch from curves. Another example would be, okay, what do you do when you have actual geometry? For example, our toy here. You can do the same basically without having to use a tool that is made specifically for Vellum, but we already see nodes that kind of turn any geometry into a simplified version with triangles, and that is the remesh node. And the remesh node works pretty well here. Ignore the problem with the texture, but you can see it turns the whole toy into a triangulated version. And if we lower the target size in the edge length, we basically get the same result as with a planar patch. We get a triangulated, very irregular rebuild of our original geometry. And if we put this into our simulation, something like this, for example, because why not, then you can see that the deformation, especially for complex stuff, will look a little bit more natural because of the more organic kind of structure of the topology. And with this, I end this video because it's fun to just look at our toy behaving like a piece of cloth and sliding over the sphere. And here we go. Okay, that's great. So I hope this was helpful. Thank you very much and see you later. Cheers.